The concept of multi-view structural graph summaries is introduced, which involves merging multiple summaries of different views of the same underlying graph. This approach aims to reduce redundancy and enable faster task completion by combining compact representations of graphs that preserve essential structural information for a given task. The authors illustrate this concept using an example from the news domain, where 3 news outlets report on a football event, resulting in 3 different graphs. The respective summaries of these graphs are then merged to create a smaller representation with less redundancy. The authors highlight the challenges of merging summaries, as simply taking the union of the summaries can result in inconsistencies and incorrect information. They propose an algorithm to address this issue and evaluate its performance using 3 graph summary models: attribute collection, class collection, and their combination. The experiments are conducted on 3 datasets: the Billion Triple Challenge 2019 dataset, a multiview source code dataset, and the International News Coverage 2023 dataset. The results show that merging 2 structural summaries has an upper bound of quadratic complexity, but under reasonable assumptions, it has linear time worst-case complexity. The running time of merging has a strong linear correlation with the number of edges in the 2 summaries, suggesting that the upper bound of quadratic complexity is not tight and that linear complexity is possible. Furthermore, the experiments show that always merging the 2 smallest summaries by the number of edges is the most efficient strategy for merging multiple structural summaries. The authors of the research paper introduce their work on merging multi-view graph summaries, emphasizing the benefits of using a combined summary model, ACC, to merge 2 summary graphs. This approach allows for the integration of diverse datasets and provides a comprehensive view of complex networks. The authors demonstrate that merging 2 structural summaries has an upper bound of quadratic complexity, but with assumptions on information storage and hash table keys, it can be achieved in linear worst-case complexity. Experimental results show a strong linear correlation between pairwise merge times and the number of edges in the summaries, indicating that the efficiency of the merging process is directly related to the size of the graphs involved. Furthermore, the authors find that merging in increasing order of size is the most time and memory efficient strategy, suggesting that a systematic approach to graph merging can significantly improve computational efficiency. The authors contribute an algorithm for merging 2 summaries, which generalizes to merging multiple summaries, and provide a theoretical analysis showing that summaries with edges can be merged in time O(e). This novel approach enables researchers to efficiently combine large datasets from various domains, such as web graphs, source code, and news datasets, and analyze them as a unified whole. In reviewing related works on graph summarization, the authors categorize graph summaries as either quotient-based or non-quotient-based and highlight the use of quotient-based summary models AC, CC, and ACC. They also discuss the importance of vocabularies in labeled graphs and their impact on merging summary graphs, as well as the applications of multi-view graphs in different areas. Finally, they mention the use of GPT-4 for generating knowledge graphs from text, demonstrating the potential for integrating natural language processing techniques with graph theory to create comprehensive data representations. In this section, the authors formalize the problem of multi-view structural graph summarization. A multi-relational, labeled graph G is defined as V, E, LV, L, consisting of a set of vertices V and a set of labeled edges E subset equal V times V. Each vertex V element of V has a finite set of labels LV, V, subset equals sigma V, and each edge E equals U. V has a finite set of labels L, U, V, subset equals sigma E, where sigma V and sigma E are disjoint sets of labels. A set of graphs G equals G1, Gn is interpreted as providing multiple views of the same underlying graph. A summary graph consists of schema information and payload, where the payload contains additional information about a schema, such as which vertices of the original graph have this schema or where to find it. A summary graph is defined as S equals V, B, E, LV, L, where V are the schema summary vertices, B are the payload vertices, and E is the set of all edges. The summary of a multiview graph G is the set S equals S1, Sn, where each C is the summary of the corresponding Gi element of G. The authors introduce the concept of graph summarization, which involves applying a graph summary model to each graph Gi element of G to create its summary C element of S. A graph summary model is a pair M equals psi lambda, where psi is a function that specifies an equivalence relation on graph vertices, and lambda is a set of task-specific payload functions. The function psi induces an equivalence relation on V, G, such that X is defined as Y if and only if psi, X, G, equals psi, Y, G. Each function in lambda defines what payload will be attached to each set of vertices X that are equivalent under psi. The authors also describe their algorithm for merging summaries S1 and S2 of graphs G1 and G2. The algorithm considers three cases for each vertex V element of G1, depending on whether V is in one or both graphs and whether the EQC of V is in both summaries. The cases are illustrated in Figure 3, which shows two summaries that are merged, with vertex colors representing EQCs. The payload shows which vertices of the original graph belong to each EQC. Merging summaries of graph data poses significant challenges, particularly when combining equivalence class representatives, EQCs, and adapting payloads. To address this, a novel algorithm is presented, consisting of three primary steps: merging summaries, correcting errors caused by EQC merging, and adapting payloads. The first step involves merging two summaries by taking the union of their vertex sets, edge sets, and payloads. This assumes that all vertices belong to case 1, where a vertex either appears in both graphs with the same EQC or appears in only one graph. In this context, EQCs are considered consistent if they have identical identifiers, which can be achieved by hashing the schema structure. The second step detects case 3, where a vertex appears in both graphs but has different EQCs. The EQCs are merged using the summary model, and the resulting EQC is added to the merged summary. This process ensures that EQCs are consistently represented across the merged summary. The third step corrects errors caused by case 2, where a vertex appears only in one graph, but the other graph contains vertices of the same EQC. Auxiliary functions are employed to retrieve all EQCs in the merged summary, determine if an EQC has members, and adapt payloads accordingly. This step is crucial in maintaining the accuracy and consistency of the merged summary. The algorithm is designed to generalize to merging n summaries, making it a scalable solution for large-scale graph data integration. Furthermore, the use of auxiliary functions enables efficient handling of different cases, ensuring that the merged summary accurately represents the combined graph data. Ultimately, EQCs without members are removed from the merged summary, resulting in a refined and accurate representation of the integrated graph data. The multiview structural graph summaries algorithm merges two summaries in 3 steps. Initially, step 1 combines the edges and vertices of the two summaries by taking their union, resulting in a time complexity of O, E, when utilizing a hash table. Step 2 detects occurrences of case 3, where two equivalence query classes, EQCs, are merged if they have the same member. This process involves searching for members in both summaries and merging EQCs, yielding a time complexity of O, E, squared. Subsequently, step 3 corrects the payloads and removes EQCs without members, requiring O, V, E, time due to the need for searching and altering each EQC's payload. However, under the assumption that all necessary information from E can be pre-computed and accessed in constant time, the overall running time of the algorithm reduces to O, E. This is because EQCs can be merged in constant time, and all required information can be accessed in constant time. The algorithm can be extended to merge n summaries by repeated application, with the runtime depending on the strategy used to choose which pairs are merged first. The proposed smallest first strategy, which merges the two smallest summaries by the number of edges, is one possible approach. Alternative strategies, such as the largest first strategy or random pair selection, can also be employed. A key benefit of the algorithm is its ability to merge different pairs simultaneously, allowing for parallel processing. The greedy parallel strategy, which chooses to merge pairs as soon as possible, can potentially reduce the runtime of merging n summaries by leveraging multiple CPUs to merge pairs simultaneously, starting with pairs of similar sizes. This makes the algorithm suitable for large-scale graph summarization tasks, providing a scalable solution for merging multiple graph summaries and enabling efficient analysis and processing of large graph data. The authors designed an experimental apparatus to test their algorithm on 3 diverse datasets: the Billion Triple Challenge 2019 dataset, the CRAN Social Science 3 Views dataset, and the International News Coverage 2023 dataset. The Billion Triple Challenge 2019 dataset contains 2.1 billion edges from 2.6 million RDF documents across 394 pay-level domains, comprising 256 million triples with 38,156 predicates and 120,037 classes. The CRAN Social Science 3 Views dataset, generated using the FlowR framework, consists of 347,867 R files with 3 views: normalized abstract syntax tree representation, control flow, and data flow. The International News Coverage 2023 dataset, created using GPT-4, comprises 450 RDF graphs covering 15 topics from 3 broadcasters, with each multi-view graph having multiple sources and focusing on the same topic. To perform the experiment, the authors calculated each graph's summary using a hash function, saved the equivalence class conditions, EQCs, with their payloads as triples, and applied algorithm 1 for pairwise merging the multi-view summaries. They excluded identical summary pairs and considered both merge pairs, S1, S2, and S2, S1, due to the non-symmetric case distribution. The authors tracked the time each merge took and merged all summaries of the BTC 2019 dataset into one summary using 4 strategies: smallest first, largest first, greedy parallel, and random. The experiments were conducted on an 8-CPU AMD EPYC7F32 with 64 cores and 1.96 terabytes of RAM, implementing the multi-view merge algorithm in Python. The authors measured the time pairwise merging took and showed how the cases were distributed depending on the vertices of the first summary in a pair. They calculated the Pearson correlation between the pairwise merge times and the 3 functions, e, log, e, and e squared, providing insights into the algorithm's performance. This research paper explores the concept of multi-view structural graph summaries, focusing on 3 datasets: Billion Triple Challenge 2019, BTC, CRAN Social Science 3 Views, CSS3V, and International News Coverage 2023, INC. These datasets provide different views of the same topic or different topics, sourced from single or multiple sources. The paper presents a detailed analysis of these datasets, including case distributions for each dataset, Pearson correlation between merge time and functions, and linear regression results. In the BTC 2019 dataset, the majority of vertices fall into case 1 for AC and ACC, while case 2 is the majority for CC. The Pearson correlation between merge time and functions such as e, log, e, and e squared are calculated, with e, log, e showing the highest correlation for CC and ACC, and e having the highest correlation for AC. In the CSS3V dataset, case 3 is the most common for AC and ACC, while case 1 is more common for CC. The Pearson correlation between merge time and functions reveals that E has the highest correlation for AC and ACC, and E log E has the highest correlation for CC. The linear regression results show that the lines for E are lower than those for E log E, with E squared not fitting the data as well as the other lines. For the INC 2023 dataset, the case distributions are similar to those of the BTC 2019 dataset, but with a higher likelihood of cases 2 and 3. The Pearson correlation between merge time and functions indicates that E squared has the highest correlation for AC, while E and E log E have the highest correlation for CC and ACC. The linear regression results show similar lines for the 3 functions, with the biggest difference between the lines for CC. Overall, this research provides insights into the characteristics and behaviors of multi-view structural graph summaries across different datasets, highlighting the importance of understanding the relationship between merge time and various functions of edge counts. Regression analyses were conducted on 3 datasets: BTC 2019, CSS3V, and INC 2023 using 3 summary models: AC, CC, and ACC. The performance of each model was evaluated through the coefficient of determination, R², which measures the variability in the dependent variable explained by the model. The results, presented in Figure 5, show that the ACC model generally outperforms the AC and CC models across all datasets, with higher R² values. This suggests that the ACC model better explains the variability in the dependent variable. Notably, the INC 2023 dataset exhibits lower R² values for all models, indicating less predictive power compared to the other datasets. In Figure 6, the distribution of 3 cases is illustrated, showcasing their frequency by pairwise merging. Case 1 is represented in blue, Case 2 in gray, and Case 3 in red. This visualization provides insight into the characteristics of the data, highlighting the frequency of each case within the dataset. The results of this study provide valuable information for researchers and practitioners seeking to understand the efficacy of these summary models in various contexts. All p-values were found to be lower than 0.05, indicating statistical significance. Merging multi-view structural graph summaries is a crucial step in graph-based data analysis. To address this challenge, researchers have developed a novel algorithm that efficiently combines summaries. The algorithm's performance is evaluated through empirical experiments, demonstrating its effectiveness and efficiency in merging summaries. The algorithm's runtime complexity is analyzed, revealing a theoretical running time of O(E)². However, under certain assumptions, this can be reduced to O(E). Experimental results show a strong correlation between the merge time and E, suggesting that E and E log E are better predictors of the measured merge time than E². When merging n summaries, the optimal strategy is to combine the 2 summaries with the least number of edges, resulting in significantly shorter processing times. The choice of summary model significantly impacts the merging process, influencing case distributions and the number of EQCs. The algorithm's generalizability is highlighted, as it can be applied to other summary models or payload functions with minimal updates. While the algorithm demonstrates promise, limitations and future work are acknowledged. Adaptations are needed to accommodate summary models considering incoming edges and extending to hop summaries. This research contributes to the development of efficient and effective algorithms for merging multi-view structural graph summaries, with significant implications for graph-based data analysis and applications. I don't see any content provided to refine. Please provide the original text, and I will create a refined version for voiceover narration according to the given guidelines.